In this video, we'll go through an introduction to high availability and load balancing of Exchange Server 2010 client access servers using Windows network load balancing. In previous versions of Exchange, our client MAPI traffic, mostly Outlook clients, went directly to the mailbox server on the local network. Now, separate to that, we also had HTTP and HTTPS traffic coming from clients such as Outlook Web Access and ActiveSync, usually coming in over the internet to our front-end servers. And if we had a particular need for high availability there, we may have deployed some sort of load balancing for those SSL connections. But as far as the internal MAPI traffic goes, that went directly to the mailbox server, and if we needed high availability for that, we would deploy clustering. With Exchange Server 2010, all of the client communications, including HTTP, HTTPS, and RPC or MAPI traffic, go via the client access server role instead of directly to the mailbox server role, except of course for public folder access. This means if we have a need for high availability, we can no longer just build that at the mailbox server level and have no high availability at the client access or front end server level. If we want high availability in our entire Exchange architecture, we have to build it both on the mailbox servers as well as on the client access servers. And in addition to that high availability, we also want to load balance that traffic evenly across our multiple client access servers. So with Exchange Server 2010, we basically have two high availability or load balancing options for client access servers. The first is Windows network load balancing, and the pros there are that it's free, it's included as a feature with Windows Server, and it's relatively simple to configure. However, it does have a few downsides. It's limited to using source IP for load distribution and persistence, and that's something we'll look at in a bit more detail shortly. We can only scale Windows NLB clusters out to 8 nodes, which may be an issue in larger scale environments. NLB is not service aware, and by that I mean that if one of our client access servers has a failed service, such as a web service, the NLB cluster is not aware of that and will continue trying to send traffic to it. It takes the entire server operating system being offline before the NLB will stop trying to distribute traffic to that node. It's also not supported to coexist network load balancing with the failover clustering features of Windows Server, which are required for DAG members. So that limits us if we want to do multi-role servers and also have high availability. And finally, there's some issues of switch flooding when we use NLB, and again, that's something we'll talk about in a bit more detail shortly. The other option is to use hardware or virtual load balancers, and these also have some pros and cons. The pros are that these hardware or virtual load balancers tend to be application or service aware, so they can detect the failure of one single service and don't require an entire node to be down before they'll stop distributing traffic to that node. They have more load distribution and persistence options, which gives us a lot more flexibility in configuring how we distribute that load, and a lot more reliability in how that load is distributed and the way the connections remain persistent. There's also some additional capabilities such as SSL offload, which again is probably only important in larger scale environments where the SSL encryption and decryption load is becoming an issue on the client access servers, and some other features such as compression and caching, which can save on traffic. And we can also typically scale hardware load balancers or virtual load balancers to more nodes, so we can run more than 8 client access servers within that load balance group. However, as downsides, these load balancers do incur additional costs and often additional skills and training, and they add another moving part to the environment, something else that needs to be managed and monitored. The concept of persistence or affinity is an important one for Exchange Server protocols and the type of communications that clients will make to the client access server. Now basically, persistence means that when a request comes from client 1, all subsequent traffic from client 1 will be handled by the same client access server. So in other words, the traffic does not flip back and forth between different client access servers, which may break stateful connections such as those made by Outlook Web Access or Outlook itself. So in an ideal world, if we had multiple clients of various types all connecting through a load balancer, their load would be distributed fairly evenly between the available client access servers, and their connections would remain persistent with that one client access server as long as it remained available. With Windows Network Load Balancing, this becomes a bit of an issue because that persistence or affinity is only based on the source IP that the connection is coming from. If that connection is coming through a NAT device, such as a firewall, then the load balancer will view all of those connections as basically being the same client. So as we can see here, even though we've got 3 different clients coming through our firewall, the load balancer treats them as just one client and sends all their connections to one client access server. Now, as you add more and more clients to this connection, you can see that the load distribution can quickly become uneven. So even with just the 6 clients shown on screen, instead of having an even distribution of 3 connections per client access server, there's 4 connections on the first client access server and only 2 on the second one. Now, whether this is an issue for you in your production environment or not really depends on the type of clients that will be connecting to your environment. If most of your clients are not coming through a NAT device, then this is probably not going to be an issue. Whereas if you do have a very large number of clients coming through NAT devices, then this is certainly something that will become an issue for you if you were using network load balancing. In addition to the concerns about load distribution and persistence, there's also the problems caused by Windows Network Load Balancing and its different cluster operation modes. And those operation modes are unicast, multicast, and IGMP multicast. And these problems basically boil down to port flooding. In unicast mode, all of the servers that are members of the NLB cluster share the same virtual MAC address for their network load balancing interfaces. Because the network switches can't associate a single MAC address with multiple switch ports, they send the traffic to that MAC address out all of the switch ports, in effect flooding every port on the switch with that traffic. Now, while this probably won't cause you problems in your test lab, this will almost certainly cause you problems in a production environment. The solution to this problem with unicast mode is either placing a hub between the NLB interfaces and the switch, so that all the traffic to that virtual MAC address has to go through the hub's MAC address first, and that allows the switch to associate it with a single port. Or you can look at configuring a VLAN, which will limit that port flooding traffic to only the ports associated with the network load balancing cluster. Or if you're running in multicast mode, you also have the problem of port flooding, because even though the network load balancing interfaces have a multicast MAC address associated with them, the network switches still will not typically associate their ports with a multicast MAC address. So once again, the traffic is sent out on all the switch ports. Now, the solutions in this case are to look at using static mappings of the multicast MACs to those specific switch ports, or switching to IGMP multicast mode. However, that is not always supported on all network switches. So in summary, you should understand that while Windows Network Load Balancing has some disadvantages, it is fully supported by Microsoft to use it when you wish to load balance or provide high availability for your client access servers in Exchange Server 2010. And that is the type of network load balancing that we'll be using in this training module. However, for some of those reasons that I've shown you just now, as well as others, Microsoft typically recommends that hardware load balancing be used for Exchange Server 2010.